Now it's the last and final step for setting up the HEC-RAS simulation is that setting the unsteady flow simulation. Here you can see the third option that's here, QOT, that says unsteady flow data. And once you open this, you get to see the boundary conditions that you already created. The upstream one, for which we can use the flow hydrograph. Here you see the flow hydrograph time and hours. You can change the date and time interval here, and you can also change the fixed time or use a simulation time. In fixed time, you can specify your own time, like you can go here and activate the right time. So we are looking at 2024 September. Probably we can run a quick simulation for like even a month. Let's say I start from the 15th or 14th night, 00 hours, and we can change the number of ordinates. Um, in for 1 hour simulation that we are doing, we can do something like 500 hours. So you can see if I do 500 hours from 15th September, it goes up to the 5th of October. So you can see at what time the hydrograph has peaked, and for the, let's say uh, it was close to 300,000 cubic feet on the 28th, I believe. So it was 28th September. You can see 28th September here around 11 hours is something here. And you can see already the units is in CFS, so it's 28300, I believe. And you can what you can do is you can give a base flow, which you can gauge from here. Probably I can call around 300 cubic feet per second as base flow. And what you can do is, for now, you can use the interpolate missing value option. Similarly, let's say I can also see at what time it's dropping. And okay, close to November 4th, it's 600, but we are looking at around 5th of October. So I can just keep, let's say, a little higher value, 1,000 value, and then interpolate this. And you can plot the data and see how it's coming, and you can modify it accordingly. And EG slope, you can give approximately 0.15 for now. And that's the initial upstream condition. For the downstream condition, you can just give it a normal flow depth that has a friction slope of, let's say, 0.025. And this is just an approximate boundary condition setup, and we can see if it really going to influence that. That's the normal depth. Is it really going to influence the study region? Then we might have to push the 2D flow area. So I was also talking about the other option that you had here. So this is the 2D flow area that you have. If you right click, you have the option to edit the flow area. So you get to edit the perimeter, you get to edit the computation points. But I just want to edit the perimeter here. You can edit the perimeter like double clicking on the lines, and you can increase and decrease. So basically, if you increase, your computation area increases and your time increases. So you might have to be careful on what region you're including. And once you make the changes, you might have to get back again to geometry data and recreate the mesh so that the mesh creation is not giving you a problem. Uh, when you start the simulation. So having set up the unsteady flow data, geometric data, and initially we use the RAS mapper to use the DEM as well as the satellite imagery to see what region we are interested in. And now it's time to run the HEC-RAS simulation. Now, having uploaded the DEM and then set up the geometric data, you can see the geometry data, the areas here, and here we mentioned the upstream condition, that is the flow hydrograph um, from the data that we have from USGS gauge, and then at the downstream end we provided its normal depth because our study area here is uh, is the regional airport, which is really further away from the normal depth. Uh, so we might not directly have the influence of the downstream condition here over the area of interest here. And third, we set up the unsteady flow data, and also we saved the data. The unsteady flow data here, I saved it as unsteady one, and then it's time for us to run the simulation now. Here you can see this is the unsteady flow analysis. Make sure you check the floodplain processing, post-processing, unsteady flow simulation, and geometric processor. You can play around the computation interval. Also, while creating the 2D area, you can make it more finer. Finer as in the spacing between dy by dx. I gave it as 100 by 100. You can make it 50 or 70 and then see how the accuracy changes. Just for the sake of faster computation, I just gave 100 by 100 and 1 hour interval uh, hydrograph is given as an input in the unsteady flow data. And now I'm going to compute, and you can see the area is being created and the layers are processing. You can see the computation message that's going on here, and you can see it's 1D unsteady diffusive wave equation set. That's the fastest. You can also run Saint Vincent equation, full Saint Vincent equation on this and see how much time it takes. But you can always start with something that's relatively easy, like a diffusive wave equation, and then go from there to complicated computation techniques. So you can see that the simulation is still running. The final results of the simulation, inundation area, the depth maps, those things will be given as a final results in the form of a TIFF file in the module, and you can go and cross-check how close your results are with mine. It doesn't have to be exactly close, but all you need to know is setting up this basic simulation and maybe a little bit about the different options that we have, like unsteady flow simulations, whether it's diffusive wave or full Saint Vincent equation, and how much it's going to be impacting. And also we'll have some questionnaire based on the results that you have, and see how you can infer. There's no one single right answer for this, or we are not trying to develop a benchmark map for Hurricane Helene for Asheville region, but just trying to explore and understand what's the hydraulic aspect behind setting up these simulations. Thank you.